Over my years of teaching methods, in recent years, this is the one I've been asked about the most. It's a really good question from 2017. Sammy visits a giant Ferris wheel. Sammy enters a capsule on the Ferris wheel from a platform above the ground. So from here, I presume Sammy jumps in there. The Ferris wheel is rotating anti-clockwise, of course, because a trig function. The capsule is attached to the Ferris wheel at point P. The height of P, so the height of this point above the ground H, is modelled by this, where T is the time in minutes after Sammy enters the capsule and H is measured in meters. Sammy exits the capsule after one complete rotation of the Ferris wheel. Best bet first off is to sketch this thing. All right, so it goes 65 units up. 65 take 55 is 10, and 65 plus 55 is 7120. All right, our period is going to be 2 pi over pi on 15, which is 30. So let's do a quarter cycle. 7.5 is the quarter cycle. 15, 22.5, and of course 30. Okay, we're cosine and we're reflected. So there, 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 there. All right. State the minimum and maximum heights of P above the ground. So this is where Sammy gets on. So min is 10 meters from the ground and max is 120 meters. For how much time is Sammy in the capsule? 30 minutes, the period. Find the rate of change of h with respect to t, and hence state the value of t at which the rate of change of h is at its maximum. All right, so let's define that function. Define f of x equals 65 take away cosine pi times x on 15 diff it. Thought that looked a bit weird. Radians. Okay, so function is called h of t, so h dash t is equal to 11 sine pi t on 15 pi all over 3. All right, and what we're going to do now is we want to find when the rate of change is at its maximum. Okay, so the maximum rate of change. All right, so there's a couple of ways to do this, but probably the easiest way to explain in 3-4 methods is to graph the derivative function. So what we'll do is we'll copy that and we'll paste it into graph and table. And let's just get this back to the default. Okay, now what we're going to have, we want it over the 30 minutes. So we'll stretch x out to about 35. Let's just jack y up a bit, 30 maybe. All right, see what happens. All right, so there's our rate of change function, and what we want is the maximum rate of change, or the rate in which the rate of change is at its maximum. So that's this point here. So we'll go analysis, gsolve, and fmax, and there it is there. So the state the value of t at which it's at its maximum. So we don't want this value here, we want t. So max rate of change is when t equals 7.5. The other thing you could do is, I quite like fmax, so you can go interactive calculation fmax for f of x and hunt between 0 and 30 for the largest value. 120 at x equals 15. Why has it done that? Because that is the original function, not the derivative. Got to be careful here. So 7.5. Okay. All right, let's go. As the Ferris wheel rotates, a stationary boat at B on a nearby river first becomes visible at point P1. So basically, if you're on the Ferris wheel, okay, if you're in this particular carriage or whatever it's called, you'll be able to see the boat at this point here, and here's the boat. Yeah. 500 meters from the vertical axis through the center of the Ferris wheel, and angle CBO equals theta as shown. Right, find theta in degrees, correct to 2 decimal places. All right, so let's jump into degrees and let's go for it. Okay, so what do I know? I know that this height here is going to be, so the vertical translation was 65, so that's going to be 65 off the ground. Let's just double check that. It's not 55, was it? Yeah, 65. And we've got 500. So what I'm going to do to find theta is go an opposite over adjacent. So we'll go tan theta equals 65 over 500. Theta equals the tan inverse. So yeah, decimal for 2 decimal places, and it is keyboard trig inverse 65 over 500, 7.41 degrees. Right, part of the path of P is given by this function here, and if you don't recognize it, that's actually a circle. All right, so what that is, well, it's not a circle, it's actually a half circle. So remember, the general form of a circle is y squared plus x squared equals r squared. And what they've done here is they've basically transposed that and written it as like y squared equals r squared, take away x squared. They've rooted both sides, which means that that is plus minus y equals, and they've taken the plus. They've taken the top half only. Okay, so that's the top half of a circle. So what they're doing is basically modeling this part of it there. Now, another way to find that is to actually graph that function to check out what it looks like. Although again, without sort of really knowing what you're looking for, it's hard to sort of know what they're actually telling. And that's what some students have said to me, is they don't even know what that's saying, part of the path of P. Okay, so they didn't know that that actually was a top half of a circle. Okay, so find dy dx of this for some unknown reason. So let's do it. Define, let's go g of x is equal to shift and root 3025 take away x squared plus 65. Now it has to be the top half of the circle as well. They can't model the whole thing because we can't derive a non-function. Okay, so the top half of the circle is a function, so we can get a derivative of that. So if g of x, let's get that version of it. So dy dx equals negative x over root 3025 take away x squared. Okay, here's where it starts to get pretty tough. All right, as the Ferris wheel continues to rotate, the boat at B is no longer visible from the point P2 UV. So basically, like, you were here, you could see the boat, and then you get up to this point here, and you're just too far across, like the boat's not visible anymore from this point. All right, the line through B and P2 is tangent to the path of P. So basically this line here runs at a tangent to g of x, or what I've called g of x, where angle OPB2 is equal to alpha. Okay, find the gradient of the line segment P2B, so the gradient of this line here in terms of u, and hence find the coordinates of P2 correct to 2 decimal places. Right, well, the gradient of this line here is going to be the same as the gradient of the tangent at point U. So what I'm going to do is this thing here, I'm going to sub u into dy dx. Okay, so that's the first thing I'm going to do is sub u, or let's say sub x equal u into dy dx. Therefore, I've got gradient m equals negative u over root negative u squared plus 3025. All right, so do that, and hence, so using this, find the coordinates of P2 corrected to decimal places. All right, so what we want to do is find the coordinates of this point. So essentially we're going to use this and some more information to find out what u is. Now the information we're going to use is that I know that this gradient here is the same as the gradient if I work it out via rise over run. Okay, so what I can do actually is work out how far it rises versus how far this function runs. Okay, so the way I'm going to do that is I will state my 2 points. Now here's my first point, which is what is it going to be, 500, 0, and my other point is going to be u, and u substituted into this thing here, all right, into the function. So that was somewhere up here. Where did I write it down? Root 3025 take away u squared plus 65. So what we're going to do is basically do the rise over the run, or y2 take y1 over x2 take x1 for these, equate it to that and solve for u. Okay, all right, so we're basically letting the gradients equal each other. Okay, the gradient of the tangent equals the gradient of this line. So let's do it. I'm going to go that, take away that, so it's root 3025 take away u squared. It's too long. Plus 65 over u take away 500 equals u over okay, all right, so a bit of work to do on the calculator here. So what I'll do is copy that. I'm going to go solve. I can just use ants equals this, which is g of x over x take 500 for x. Now I think this will work. 2 decimal places. All right, x equals 12.997. So we'll go u equals 12.9974 dot dot dot. So the coordinates is what we want. So it's going to be 12 point, no, it's going to be 13 rounded to 2 decimal places, and I would put those 2 zeros in there. And what we'll do then is we'll slam this number here into g of x. So we'll do g of this value to get v. And it's 118.44, corrected 2 decimal places. So making sure that you're using the most exact form to sub in. Don't sub in the 13. Okay, find alpha in degrees correct to 2 decimal places. So we want alpha. All right. The way we're going to do that is a little bit complicated, but what we'll do is we'll turn this into right angle triangle, right, where this line here is going to be 500 take away the value of u, which we just found out to be 13. Okay, so what we'll do is we'll go, it's going to be opposite over adjacent. So it's going to be tan alpha equals 500 take away 12.997, so 12.997 dot dot dot, all over this value here, which is going to be 118.44 dot dot dot. Okay, so alpha equals, so via inverse tan again, and we're still in degrees, we're going to go 500 take away this over whatever's in the ANS slot. Doesn't sound right. All right. So yeah, I mean, good case in sort of error detection here, and if you can spot the error, opposite over adjacent means that these should be flipped. So stupid mistake by me, but if you sort of know what your numbers are going to be like, you kind of realize that alpha can't be 76 degrees. Are you kidding me? All right, so just got to remember how to write this out again. 118.44 dot 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 500 take. I mean, all of this is just for 1 mark. They're just looking for alpha anyway, so you didn't even have to write this down. But what do we got? 12.9974 dot dot dot. So let's flip these around. So I'll just put ANS over and get rid of it from here. And that sounds a bit more reasonable. 13 point, what is it, 2 decimal places, 6, 7. I wonder how many students got done on rounding errors here, because there's heaps of them. All right, hence or otherwise, find the length of time to the nearest minute during which the boat at B is visible. All right, so you may notice some continuity issues with this video here because I'm having to re-record this last question. I actually recorded it at the end of this video, but forgot to hit unpause. So I'm just having to tack this on the end, and I'm working on a version of this that I've previously worked. So I'll still be able to answer this last problem, but some of the things might not look totally continuous to the rest of the video. Right, so let's just finish this off. So what I need to do is, the way I'm going to process this is I'm going to draw a line from here to here. And the reality is what I'm looking for to answer this last problem is this angle here. Let's call this, I don't know, beta or something like that. So if I can work out this angle here, then I can express that as an angle out of 360 degrees. So that angle out of 360 and multiply it by the time it takes to do 1 revolution. And basically I'm going to get the time period for which this boat here is visible. Okay, so this is the angle that I'm going to work on first, because if I know this, I can use that plus 90 degrees, remove that from 180, and I'll get beta. So this I know will be alpha, which I've worked out in this question, which was 13.6. So there is that one there. I'm going to start with alpha, and I'm going to remove this one here, which is 7.41. So I have to retype this, but I'm going to grab that, copy it, and paste it down there. Right, so that means that this angle here is 6.2624 dot 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 dot. All right, so the way I'm going to work out beta then is go 180 take away 90 plus the answer, which means that beta is equal to 83.737 dot 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 dot. Okay, so the way we're going to do this then is go, all right, 83.737 dot 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 out of 360 degrees multiplied by, so again, what we're doing is basically working out the fraction of 360 degrees or 1 revolution for which the boat is visible. We know that the period or 1 ride lasts for, I think it's 30 minutes. Yeah, 30 minutes that 1 revolution takes place. So then we're going to multiply that by 30. Right, so let's do that. We'll take that, divide that by 360, and multiply it by 30. And what we're going to get is 6.97813 dot dot dot. To the nearest minute will be therefore 7 mins. All right, so there is that final problem. Fairly difficult if you don't sort of start chopping up this into manageable right-angled triangles. But yeah, the whole problem was certainly a tough one.